Of the afternoon is Professor King from Nottingham, and we'll talk about wave propagation in non-homogeneous semilinear reaction-diffusion.
Thank you. Okay, so this is joint work with Carlotta, who's now in Madrid. I'm talking about much simpler equation than almost anybody else, and I want to make a couple of important disclaimers first. So this work was provoked by some stuff in the physics literature. I was far from being on top of the physics literature, and I mentioned one aspect of that right at the end, but I'm conscious I'm not at all on top of the analysis literature. And indeed, embarrassingly this morning, I found a paper by Evans and Tsoukanidis that slightly disrupted lunch. Perversely, that's one of the reasons I want to talk about it here. So I would appreciate feedback from the point of view of what's been done by analysis. With this type of problem, I'm never quite clear whether to go for full generality and illustrate it by special cases or conversely. So here I've gone for sort of a halfway house. I'm going to stick the spatial non-homogeneity in there. I'm going to keep that essentially entirely arbitrary, but I'm going to put the small parameter in the sort of hyperbolic scaling places, and I'm going to take psi not to depend on epsilon. So those are restrictive assumptions. I'm doing the monostable case, the Fisher KPP kind of case. As almost all of you will know, the standard question then is a small perturbation will drive you from the original unstable state to the stable state 1. The disturbance will spread with some speed. And when in the spatially non-homogeneous case, the speed will depend on time. So the key question is, how fast does that front go? That's what the talk's about. Here's the conclusion in advance. There are different mechanisms of selection. Which one applies depends on whether psi is increasing or decreasing. A more strident summary of this talk is that it's in some sense an accident that the derivation of the Fisher wave speed in most mathematical biology books gives you the correct answer. There's something very special about the borderline case where psi is a constant. So this statement will need explanation, and for this reason I need to actually say quite a lot about the ordinary Fisher equation, because I need to explain what the selection mechanisms are. And the other point is that this, in some sense, isn't surprising a priori that there'll be differences. You only start to see why it might be surprising when you do the middle case. Okay, so there's the conventional Fisher equation, repeating the points from before, but now the wave speed at large time is a constant. So the way we teach these things in formal asymptotics or whatever is typically by linearization approaches, and there are two of them around. I guess both of them are used at undergraduate level, so I want to go through both. The point I'll then come to is it's a coincidence that the two give the same answer, and that is another summary of the talk. Okay, so rewrite the PDE in traveling wave frame and assume it's dominated by the convective derivatives in that frame, reduce it to this ODE here. So that'll be the first linearization approach, will be the linearization of that. I don't linearize straight away, I do the phase plane, but then I linearize. So that's the thing rewritten in phase plane variables. The stable steady state is a saddle within this traveling wave formulation. The unstable steady state flips from stable node to degenerate node to stable spiral as you decrease the wave speed. That's reflected in this linearization, and here's the rates of decay. Critical damping is the most important wave speed here, c equals 2. Here's the decay for larger wave speeds. And focus on what that A minus is, because I'm going to come back to it in a second. A minus multiplies the slow decay in the far field. So what does the ODE tell you about the wave speed? It tells you that a non-negative and therefore physically realizable wave only exists if the wave is fast enough. You can construct them numerically by shooting from the saddle from minus infinity, so you shoot out here. You'll always end up in here for C positive, but not necessarily with with U remaining positive. Okay, so if C is large, it just comes in on the slow decay. For the so-called pooled or linear selection case, that quantity A minus of C remains positive for all C bigger than 2. So whenever C is bigger than 2, the picture looks like this. Then you go down to the degenerate node where it goes in as fast as it can, critical damping, and below that the solution's on physical. So this is the smallest realizable wave speed in the pooled front case. The rest of my talk will be exclusively about pooled fronts where linear methods apply, but I want briefly in passing to those of you who don't know to see what the push front is, because that's the case where the linear methods don't apply. So the push fronts occur when that coefficient A minus goes through 0 for some c bigger than the supposedly minimal speed 2, which means the smallest realizable speed is this one here, which is speed bigger than 2. That one's associated with coming into the node along the fast decay rate, and then it flips back and comes in on the wrong side. So if the nonlinearity is strong enough, this regime applies in the phase plane, and this is the smallest realizable speed. The upshot of that for which wave is selected, it's helpful to generalize the problem, to consider the class of initial data with this kind of decay at infinity, where lambda is an arbitrary positive constant. If you try and match this with the decay of the traveling wave, you find that if lambda is less than 1, it's associated with the slow, lambda is associated with slow decay. Conversely, if lambda is bigger than 1, it's associated with fast decay. And the result for the wave speed for for pulled fronts with this type of exponential decay is that if it decays fast enough, it goes at this speed 2. And the reason I'm going through the details of this will become clearer later. If lambda is smaller, if the thing decays slowly enough, you can drive it faster. For push fronts, the picture looks like this, and the minimum wave speed is associated with fast decay here, and it's bigger than 2. So that's the ODE argument for linearization. There's a PDE 1-2, which gives the same answer, but it's not the same argument. And again, that's the point of the talk. So if I linearize the PDE, and I'll do it in 2 ways, Kendall, although he was more systematic than I'm going to be, argued you chuck away the nonlinear term and solve this thing. You can remove that by extracting e to the t, and then the large time solution, of course, is the Gaussian, so it's given there. So you argue that in the middle, where this thing's become exponentially large, the nonlinear term comes in and saturates it, so it shuts it off here. But out the front, the linearization does apply. So you can stare at this exponential and conclude that this solid curve, where the solution is exponentially small, corresponds to mod x over t is less than 2. So again, you're extracting the same wave speed here as t equals 2 is the transition between exponentially small to exponentially large. In the physics literature, much more complicated problems than this are solved, but the argument is given here. It's typically done by Fourier transforms, which of course only works for the constant coefficient case, which sort of impinges on the rest of the analysis. There's the Fourier transform representation of the solution in this simple example. The large time behavior is given by saddle point estimate, or equivalently, you evaluate the group velocity. It's given by this, and eta equals 4 is again the transition. So eta is x over t. So that's one PDE approach. I don't like this final one because you're Fourier transforming, you're linearizing and then Fourier transforming, so you're assuming the linearization holds everywhere and including in the middle where it clearly doesn't. So I much prefer to view this tail behavior here as associated with the WKB solution to the PDE. So the second ODE approach, PDE approach, and the one I'm going to use subsequently, applies Liouville-Green, usual exponential ansatz and dominant balance in the form of an iconal Hamilton-Jacobi equation. That, of course, is constant coefficient because the original equation is. Time is the large parameter, so the solution for large time is necessarily self-similar, it's of this form. And for this, crucially, just for this constant coefficient equation, the self-similar form corresponds to Clairaut's form, and therefore this ODE has 2 classes of solution. The general solution associated with the exponential decay I alluded to earlier, lambda eta, and the singular envelope solution, which is the thing the Fourier transform analysis or whatever picks out. And it's the one way of seeing why the homogeneous case is critical, is borderline, is that this thing is Clairaut. So you get these 2 solution classes and you can pass smoothly from one to the other. Okay, so the relevant ray families for the classes of problem I've referred to, exponentially decaying initial data with coefficient lambda, the rays look like this. I draw them in a second. For much faster decay, the rays are an expansion fan coming out of the origin. I'll later actually take the front to start at x equals a. But in terms of what I talked about later, a would be 0 here, expansion fan from the origin. The next statements in words are summarized in a picture in a minute, so I won't repeat them. So what do the ray families look like? So here the WKB analysis does apply, even though the linearization doesn't apply everywhere, because as you track along these rays, you stay in the linearized regime. The solution stays exponentially small. Here's another way of seeing this transition at lambda equals 1 between the lambda small, where the solution's selected by the initial data. Here are the rays coming from the initial data into the wavefront. If lambda is bigger than 1, it would tell you that the traveling wave looks like that, but it can't do because the final trajectory corresponding to the initial data is moving faster than the wavefront, so it can't pull this thing along. And therefore, you don't select the faster wave in that case. The case where you do get the, for faster decaying initial data, the relevant ray solution that determines where the wavefront is as stated, the expansion found from the origin. And the important thing, again critical about the spatially homogeneous case, is that the ray here runs parallel to the wavefront. The wavefront is itself a ray. That doesn't happen as soon as the problem's non-homogeneous. Finally, if you take the fast decaying solution coming out of the wavefront, and that can only happen for push fronts, the rays run out of the wavefront and determine a different set of solutions out here. But this can only happen for push waves. So that's the summary, and I'm trying to rush through it because I want to get onto the thing I'm actually talking about. So there are these two, in ordinary fissure, there are these two different mechanisms, hand-waving, if you like, mechanisms, but justifiable at whatever level you prepared to believe them, which both give the same answer. So one is to apply the repeated root condition to the travelling wave ordinary differential equation. In other words, it's a degenerate node, and that's the pulled front argument. The other is to use the geometric optics argument and track the f equals 0 level set at the relevant iconal equation. So as I keep banging on about, these two things give the same answer in the heterogeneous case. In the homogeneous case, they don't in the heterogeneous. So I'm now going to get on to heterogeneous. I will briefly at the end talk about the special case which illustrates the point, where there's parallel behavior in the heterogeneity. Then n less than 0 corresponds to decaying psi, and to warn you in advance what's going to happen, in this case one gets the ODE argument, in this case one gets the PDE argument. So it splits the arguments that give the same conclusion when psi is a constant split when it's not. So the classic case is non-generic in that sense. Okay, so on to the thing I'm actually talking about. There's two regimes I've got to deal with. I better remind you possibly of the original statement of the problem. So remember the epsilon is in here. So if I want to look in the frame of reference to the wavefront, I'm going to scale x, I'm going to magnify x by a factor of epsilon to pull this thing in, and then the convective derivative will pull that in as well. Okay, so with that change of variables magnified appropriately, the dominant travelling wave balance is the one recorded there. We've got the non-homogeneity here, but now it's just parametrically in terms of time. I don't know what s of t is, but this just does depend on s. So I factor that out by making this change of variable to rewrite the travelling wave in a problem in exactly the same form as it takes in the homogeneous case, as long as I define some wave velocity in this form. That will typically, no, I won't say that. So that this defines my c, which in general will be a function of t, but it does remain to be determined. And I've already set out two possible mechanisms to determine it, and I now need to explain which applies. So the remaining region is the one ahead of the wavefront where the solution's exponentially small. So a method invented in Nottingham and I think Paris, I assume Paris simultaneously, and then rediscovered by a lot of people later. There's the usual WKB ansatz. Here's my iconal equation generalized to the non-homogeneous case. I'm going to solve that by the standard geometric optics method, so by writing down Sharpie's equations, the ray equations, and they're recorded at the bottom here. So we compute f evolving on rays, which are determined by these two ordinary differential equations. On rays, this quantity is a constant because q is, and that's the PDE. Okay, so I'm now going to try and, almost the whole of the rest of the talk is about the properties of these rays, so I'm going to try and talk you through the relevant aspects of them. The PDE selection mechanism determined the front as being the level set f equals 0 of this Hamilton-Jacobi formulation. So here's one possible selection mechanism, and I'm going to track through the implications of that. So at this level set, the Hamilton-Jacobi equation takes this form. So one has a quadratic for p, which is df by dx. Here are the solutions to that quadratic, and they immediately imply the minimum. The wave speed certainly at least has to be the one determined by the repeated root condition, as we've already seen, but it could be larger than that. Okay, x dot is equal to 2p. So if we compare how the velocity of the rays at the wavefront are going compared to the velocity of the wavefront itself, if this term is positive, the rays go faster. If you take the negative square root, they go slower. So dealing with the second of those first, here's the rays coming into the wavefront associated with slow decay. The travelling wave, if it's going faster than the minimum speed, will have slow decay. So that's a plausible matching mechanism. The second case is not possible. With the positive square root, the rays are coming out of the wavefront. They're associated with fast decay, and so they can only occur with push fronts, the case I'm not dealing with. Okay. So that was the general case where this inequality holds. The other interesting case is where it's equality holds here, so we're on the repeated root condition. So if we're on the repeated root condition, the velocity of the characteristic is the same as the velocity of the front, and we have to go to higher orders to see which way the thing's going relative to the wavefront. So compute the acceleration of the wavefront. It's negative if psi is decreasing, and that's the case where this applies. Whereas the velocity of the ray actually is the same quantity with the opposite sign. So now in the psi increasing case, we can't have the front going with the repeated root speed. If it was to do so, these rays would be left behind the wavefront. You'd have a solution out here which didn't make sense. Conversely, if psi is decreasing, the rays can come out of the wavefront. They start off tangential to it, but propagate in front of it. And in that case, they can supply the missing solution you need ahead of the wavefront. The final piece of the jigsaw, before I put together a conclusion about how the speed is selected, is to consider the initial value problem, just not the local behavior at the wavefront. So for definiteness, although the conclusion is much more general, I'm going to take the initial data to be 1 to the left of some point and 0 ahead of it. There's the initial conditions corresponding to the Ray ordinary differential equation, and the one for how f evolves can be rewritten in that form. So what happens on the various rays? Well, P is an arbitrary positive constant, so P0 determines which ray in the expansion fan you're sitting on. If P0 is large enough, this thing certainly starts off positive, whereas if it's small, it'll start off negative, and the relevant condition is written down there. So I'm now going to be slightly more prescriptive about psi, although, again, the extra conditions I'm putting in just to save myself explanation rather than because they're central to the argument. I'm going to take psi to grow unboundedly in the first case. So in the increasing case, psi will grow unboundedly as x goes to infinity. Conversely, in the decreasing case, it'll go to 0. So we now split it into the two regimes. Right, so case B is where psi dash is negative. Therefore, P is increasing. Therefore, not only is x increasing, but x dot is increasing. So the rays go faster and faster. In this equation, P is increasing, psi is decreasing because x is increasing. So both of these terms are going in the same direction, and f grows faster and faster, which means on any ray, f ends up being positive. So the expansion fan picture looks like this one at the bottom. The level set f equals 0 schematically is shown by the dashed curve. That is one possible location of the wavefront, but it can't work here because any ray arriving on f equals 0 has gone through a region where f is negative. If f is negative, the WKB solution is exponentially large, so the linearization doesn't apply. Equivalently, the rays coming out are associated with fast decay, so they can't work for pulled fronts. So this picture doesn't work when psi dash is negative. However, it does work if psi dash is positive, or I wouldn't have told you about it. So here's the corresponding picture. In this case, P dot was minus psi dash, so P is decreasing. X dot is positive as long as P is positive, but it gets less and less positive as time increases along characteristics. So here's what the characteristics schematically do in this case. They come out of the initial front location. They swing round with F initially increasing on these rays and then decreasing again to 0. On these rays, F decreases for all time. So this is in the nonlinear regime. But here's a plausible location for the wavefront. F has gone, the solution is exponentially small as you track down here, but then increases again to become of order 1 and identifies the front location. So in that second case, the the geometric optics does give a possible way of selecting where the wavefront is going to sit. So the rays are associated with slow decay here, as the previous pictures implied, and therefore they will match into a wave that's moving faster than the minimum wave speed and sitting along this dashed line. So that's a self-consistent scenario for where psi is increasing. I haven't yet got a self-consistent one where psi is decreasing, but I've only given you one alternative selection mechanism, which is the repeated root case, and that is indeed the one that applies. So that, as I've said, that case doesn't work for psi dash negative. Here's the repeated root condition. The wave goes at this speed. As I've explained, in this case, when psi dash is negative, rays come out of the wavefront, initially tangentially, but then run ahead of the wavefront. So to building up the complete picture, in this case, there are these expansion fan rays from the initial data, but F is strictly positive on these, so the solution is exponentially small and they can't pull out a wavefront. The only way of filling in the gap here is to have the front going at this speed and producing rays that come forward from it and determine the solution elsewhere. So that's the second set action mechanism, and the proposal is it does indeed apply when psi is a decreasing function of x. So to summarize, I'll finish slightly early, but then go through, make a few remarks about a special case where we've done the analysis in complete terms, because it can be completely classified. So we do have these two alternative mechanisms, and then here's the borderline case I started with. So if I start with B, in fact, this is the last one I talked about, if psi is decreasing, the selection mechanism is this repeated root condition, essentially a local argument, an ordinary differential equation argument based on the travelling wave ordinary differential equation. However, if psi is increasing, you can't just solve a single local ODE for the wavefront. You have to find the full solution to this PDE and track from that solution how the level set F equals naught is evolving. But one upshot of that is, in this case, the wavefront has to go faster than this. So here S dot is greater than 2 root psi. Finally, in the Fisher case, I've already alluded to a number of respects in which it's exceptional. And an equivalent way of restating some of the ones I said earlier is here is the ray equations in the spatially homogeneous case. And in particular, F dash doesn't change on the rays. So the rays are straight lines. If you choose the ray on which P starts off being 1, F doesn't change on that ray either, it stays 0. So the wavefront is itself a ray, and it's that means it lies at the intersection of these two different selection mechanisms. They give the same answer, and this case is entirely exceptional. So there's one or two loose ends to tie up. The first is I've only talked about the case where, separately, the cases where psi is increasing or psi is decreasing. So what happens when you switch between the two, as you're perfectly entitled to do, at a minimum of psi, where psi switches from being negative to being positive, did I say psi dash? Psi dash switches from being negative to positive. If you recall the argument, the selection mechanism where psi dash was negative entirely failed where psi dash was positive, because the rays from the wavefront went in the wrong direction. And that means there has to be an immediate switch in this case. You switch from the repeated root selection criterion to the geometrical optics selection criterion as you cross psi dash is 0. And in terms of the ray picture, what happens is the rays that emanated from the wavefront where psi was decreasing swing back round and bang back into the wavefront with F equals 0 here. So increasing and then decreasing again as before. The situation where psi is a maximum is different because the switch isn't immediate. So here are the rays associated with psi dash being positive, banging into the wavefront and being associated with fast-moving waves with slow decay. You hit this switch here, but there's still rays coming into this vertical dash line from the left. They're carrying solutions on which F equals 0 in front of where you'd get F equals 0 from the repeated root selection condition. And the switchover now occurs on the ray which comes in tangentially to the wavefront. Beyond that, there's no rays coming from over here, and instead the rays have to propagate out of the wavefront. So there's a deferred switch from geometrical optics to repeated root. And of course, the thing going up and down, that second switch may not occur at all. Okay, a few concluding comments. The case we've done in gory detail is the special case I alluded to before. So this case will at least illustrate the two regimes. N positive is web size increasing, N negative size decreasing. The reason I'm explicitly flagging this is to talk about this dependence on lambda. So when I talked about Fisher, and it's a standard case that's done, this formula is wrong, that should be a 2 on the bottom. So when n is 0, this coefficient n plus 2 over 2 is 1, and that was the case I talked about for Fisher, ordinary exponentially decaying initial data, and again that's all in standard books as well. So this power law, when corrected, is the appropriate generalization to this power law case. Here's the Hamilton-Jacobi equation in this case, and the virtue of having a power law here is the solution you need is the self-similar one, which takes this form. So you're back in a situation where you can completely characterize things for all time because it's all embedded in a single function, capital F. So how does the scenario depend on lambda? I'm sorry, these pictures didn't join up terribly well. This is another respect in which you can make a clear distinction from the critical case, the borderline case. So the borderline case I've already alluded to, as lambda increases, you come down to the minimum speed, and then you sit on that minimum speed. The slope of this curve is continuous at this point. It's 0 coming in from both sides. The situation for side decreasing is, in some senses, similar. It comes down to speed 2, and here's how the speed's defined in this more general case. The speed is 2 at some critical value of lambda, and then it just sits on the minimum speed. The only real distinction is in this case, C dash is continuous. In this case, it comes in with finite slope and then switches abruptly around the corner. The more different case is web size increasing, and the wave velocity is more like this curve. So there's two clear differences. One, it doesn't come down to the minimum speed for any finite value of lambda. There's no abrupt switch like there is in these two pictures. And the minimum speed is itself larger than the one determined by the ODE. And then the speed is larger than 2. So to sort of wrap up the special case, here's the schematic of the things that can happen. And this revisits a number of points from earlier. So if lambda is less than this critical value, and the critical value is infinity in the increasing psi case, you find the front by a red. These two methods are linear. Sorry, these three methods are all linear. This one is based on the WKB. This one is based on the ordinary differential equation. So if the initial data decays slow enough, the wave speed is determined by that initial data by tracking the rays that come from the initial data. If psi is increasing, you track the expansion parameter from the initial data and find where f is 0. So that's fast decaying initial data, you get it by WKB. Conversely, if psi is decreasing, you get the wavefront location by using the repeated root condition on the ODE. These two conditions give the same answer in the special case. This is one of only two other mentions I'm going to make of push fronts. These arguments were all linear because they assumed that the travelling wave with slow decay did exist if the wave was faster than critical. Push fronts, the wave is faster than critical, but it has fast decay. So the arguments I've given don't apply. They can be patched up, but there's no way around explicitly solving the nonlinear ODE to find the wave speed, except in special cases where you can write down the answer. The reason I'm flagging this now is the transition between these cases is different. This goes at the repeated root condition, and that flips to a push front as soon as that front is faster than that one. This goes faster than the repeated root condition, so the transition to a push front occurs only for a nonlinearity that in some sense is more nonlinear than it is in this case. So I think final slide, the other issues that I'm not going to elaborate on the details of. Isaac Newton put me in the same office as Vincent, which is very useful because he with Sergei and others have a paper that covers some of the same ground as this. I apologise that I haven't fully digested it, but I think the concrete examples in there were where psi dash was positive. So it corresponded to one of my two regimes. Second point is the same arguments go through in the higher dimensional case. There are some obvious additional complications, but because you can formulate it as a first order PDE, there's lots of ways of dealing with it. But some extra things can happen, of course, because if you pick size appropriately and your wavefront is something like this, you can have different selection mechanisms applying on different parts of the wavefront. So say geometrical optics down here and repeated route up there. I've sort of implied how that goes in the special power law case, but more generally you can treat these two, but you do need to take the analysis slightly beyond what I've described. And finally, for Fisher, there's a very famous correction term to the leading order velocity 2t. It converges very slowly to that velocity 2 because the correction term is logarithmic. In terms of formal asymptotics, that logarithmic term is determined by a transition layer in which the dominant balance in the original equation reduces to the heat equation. The situation with these correction terms where psi is non-positive again differs, so that borderline case is non-generic. And the case where it's really worth doing is where psi dash is decreasing, and then the dominant balance in the transition is the area equation, and the coefficient of the correction term is to do with a 0 over the area equation. So those were the things I wanted to say. Thank you.
Question or comments? Yes.
Oh, just one question. A while ago, Friedland showed very interesting result when your function psi increase fast enough, then you might have ignition point ahead of the reaction plan. Have you observed this?
I'm vaguely aware of that. I haven't. I assume what he must have done is, but he can't have taken compactly supported initial data because there would be nothing to trigger the second point. Otherwise,
second point it's tails, because it's a combination of tails and higher reaction rate.
Yeah, no, I do understand then. Yeah, no, I understand. I haven't. Yeah.
Approach. That's why I'm asking.
Yeah, I haven't looked. That is interesting.
Question? Okay, well, thanks again, the speaker.